Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of the second module is Working Principles of Shear Viscometers. The previous lecture we have seen the working principles of capillary viscometers, that is the expressions for the shear stress and shear rate for a fluid flowing through a capillary viscometer. Those working principles we have derived. But the question is that whatever the working principles that we have derived, so we make use of the data q versus minus delta p and then convert them in terms of shear rate and shear stress respectively using the respective equations. So, whatever that rheological information is coming, is that reliable or not? Is there any possible source that may be changing the rheology from one case to the other case for the same fluid? Those things one has to check carefully. Right. So, this particular lecture is followed by the previous lecture. We will be discussing the sources of errors, if at all some sources of errors are there, what are they, and then how much significant are they, how to make correction methods if we cannot avoiding in the sense by making adjustment in operating conditions like that, or making small changes in design, how can we get over through these errors. If not possible, then how to make corrections. Those things we are going to see in this particular lecture. So, first we list out the sources of errors. Several sources are possible in measurement of rheology using capillary viscometer. The very first and foremost important thing is that end effects, right? End effects in the sense entry and exit effects. Why these entry and exit effects are important? They may be causing some kind of error, because the working principles whatever we derived in the previous lecture, we have derived for the case of fully developed laminar conditions, right? Steady state fully developed laminar conditions. Let us say if the flow is not fully developed, then definitely there will be a kind of possible error, right? Okay. Experimentally when you are doing, if the flow is not fully developed, that means that will be inducing some kind of error, right? If the flow is not laminar, the experimental conditions whatever the q versus delta p information you got, you convert in terms of the Reynolds number. If you see that Reynolds number is beyond the laminar flow conditions, so whatever the rheological information that we get using the working principle that we developed in the previous lecture, they will also induce some kind of errors, right. So, one important effect is the entrance and exit effects that is causing because of the fully developed cases. So, whatever is the length of the pipe, especially if the length of the pipe is small, flow is not generally fully developed. That is what we have seen. When we take the fully developed conditions, we mention that it is the length of the geometry is infinitely long, so that the end effects are negligible. That is what we are saying. But what happens, whatever the length is there like this, this is let us say barrel through, and then there is a capillary connected, that is what we have seen. So, even if the length is large enough, what happens near this this area, entrance area, because this is the length of the capillary, and then we consider this point as the entry point. So, at this point we will never have a fully developed flow, and then because of that one, the pressure drop will not be same as the pressure drop under fully developed conditions. However, if you have a kind of a larger pipe, it is possible that at the exit effects may not be contributing much in the end effects. So, that is one thing, right. So, we are going, that is the one possible error. So, that is the mostly the entrance effect that is going to have a kind of influence or the causing some source of error in the rheological measurements using this capillary viscometer. So, those errors we incorporate in this end effects, right. So, we are going to see what are these end effects, how we can overcome them. Then wall slip effects. Wall slip in the sense the velocity at the wall, usually what we in the working principles when we have derived, we have taken this at wall, that is at r is equals to capital R, we have taken Vz as is 0, and then at the at r is equals to 0, it is maximum, that is what we have taken. But we know that for a small geometry like flow area, the passage area, that is the diameter, if it is very small, right, then in general at the wall we will not have a kind of 0 velocity, but we will have some kind of slip velocity, right. That is slip velocity that is occurring because whatever the fluid layers at the wall are there, they will be depleted, and because of this depletion, the viscosity at this wall, the viscosity of the fluid at this wall would be smaller compared to the bulk viscosity. So, because of that one, shear rate would be very much smaller compared to the expected shear rate if there is a slip velocity, right. So, that is the another important one that we are going to check. Next, sometimes kinetic energy losses associated with the acceleration of fluid from barrel velocity to the velocity in capillary. So, if the velocity flowing through pipe is large enough, in general there would be kind of kinetic energy losses, and also the head of this fluid in the barrel, if it is changing as the fluid is drawn through the capillary, and then change in the variable head, that is change in the head of this fluid in the barrel, that would also cause some kind of errors. And sometimes, as I mentioned, the working principle previous lecture that we have developed, they are valid only for the steady state fully developed laminar conditions. So, any departure from laminar condition, they will also induce some kind of errors. So, we are going to see those things also. And then viscous heating effects, if the apparent viscosity is very large and then velocity is also very large, then it is possible that the viscous heating may take place, and then viscous heating may contribute to the different velocity distributions, and those things are also going to be show some kind of errors. These are the some of the errors, there may be other errors also, but these are the primarily important errors. So, we are going to find out very soon that these two effects are very much important, and then you cannot avoid, you have to make a kind of corrections, and then what are those corrections we are going to see. Kinetic energy losses, and then this whatever the departure from the laminar flow conditions can be reduced so that they can be avoided if the velocity is maintained small. If the small velocity, if you can maintain through capillary, then what happens, the kinetic energy losses will also be less, and then deviation from the laminar flow condition will also be not existing, right. So, by this operational conditions, these two things may be reduced. Okay. Then viscous heating and variable head in barrel can also be reduced if you take cross section area of the barrel is very much larger than the cross section of the capillary. In such cases, you can avoid the effect of the error due to the variable head in barrel. These things can be avoided, right. So, some of these errors, as I mentioned, may be minimized by suitable design of viscometer. Let us say if you have the cross section area of the barrel very much larger than the cross section area of the capillary, then effect of variable head and fluid friction that is causing viscous heating etc. in the barrel can be neglected, right. And then if you change the operating conditions, like if you operate viscometer at flow rates where changes in kinetic energy of emerging stream from capillary are negligible compared with other terms in mechanical energy balance for the system. So, by operating at smaller flow rate, it is possible that you can avoid this effect of the kinetic energy losses may be small in comparison with other terms in the mechanical energy balance, right. So, from this discussion what we understand, these are the two end effects, and then wall slip effects are the kind of very common and then severe sources of errors, and then we see what are the possible correction methods. First we have to find out how much significant are they, then how to make the correction adjustment without losing the reality of the rheological picture of the fluid. Okay, that is what we are going to see now. So, first one is the end effect, right. So, end effect is usually because of the entry effect and then exit effects, and then we know that due to the fact that near entry of the capillary tube the flow cannot be fully developed, and then obviously pressure drop will increase if the increase compared to the pressure drop under the fully developed conditions, right. So, but whatever the contribution of exit effect in the end effects are there, they are usually much smaller compared to the entrance effects. So, their contribution of exit effects in the overall end effects is very much smaller compared to the contribution of the entry effect, right. So, that can be in general neglected. Okay. And then this magnitude of entrance effect, it also depends on the nature of non-Newtonian fluids, whether are we having the generalized Newtonian fluids, time independent time dependent or viscoelastic type of fluid, all of them having different magnitude of entrance effect. Okay. So, but however, for generalized Newtonian fluid or purely viscous fluids, something like shear thinning fluid, shear thickening fluid and viscoplastic fluids, it has been found if L by D ratio is more than 100, one can say that end effects are negligible. If L by D is greater than 100 for these fluids, it is believed that the end effects are negligible. However, analogous information is not available for viscoelastic fluids. Viscoelastic fluids, how much the value of L by D should be there, that is not clear, but however, it is believed that L by D value would be much more higher than the 100 value. So, next thing, the how to make a correction for this end effects. First of all, whether some kind of effects, end effect or wall slip effects, whatever the source of errors we are expecting, is that existing or not, that one has to check. How to check? When we do the capillary viscometer experiments, what information we get? We get Q versus minus delta P information, and then by using the tau W is equals to minus delta P by L R by 2, and then gamma dot is equals to 8 V by D, and then V we can get from the volumetric flow rate divided by the cross section area, right. So, this information when you plot for different size of capillaries and then different lengths of the capillary, tau W versus gamma dot, when you plot for all these cases, if the curves are superimposing, then we can say the effect of the length of the capillary or the diameter of the capillary is not there, and then these things, the data, whatever the Q versus delta P information data is there, that is free from the such kind of effects, and then whatever the corresponding rheological behavior you get, that would be the true rheological behavior. That is what one has to make confirmation before going to check any sources of errors and then corresponding corrections, because if any source of error is there due to the length, that will be causing a kind of entrance effect. If at all there is a source of error because of the diameter of the capillary, then that would be causing a kind of slip effects. So, that is how we have to see. If you find that they are not superimposing, then you have to check for the individual errors, right. So, one simplest thing before going to check whether the entrance effect or exit effects are there or not, you can see if the fluid is not expected to have any elastic nature, and then you check L by D of the capillary, if it is more than 100, you can say that there may not be any end effects. That is the simplest one. Okay. Let us assume there is a kind of possibility of end effects, entrance or exit effects. So, how to incorporate? So, exit effects are in general smaller compared to the entrance effects. So, let us not worry about the exit effects, they are negligible compared to the entrance effects. So, we see a method, correction method for in order to incorporate entrance effects now. Okay. So, here this method is proposed by the Bagley, right. What they have suggested? They have suggested whatever the Q versus minus delta P information that we get from capillaries, we should get at least for 3 different type of capillaries having same diameter, but different lengths, L1, L2, L3 like that. Now, you see here that one particular data minus delta P versus Q is reported here for different lengths, we are seeing that they are not superimposing. So, then obviously, their corresponding tau versus gamma dot information will also be having the different values expectedly, right. And then we can see here as increasing length for a fixed volumetric flow rate, pressure drop is increasing. Okay. Now, what we do this data? We rearrange this data. We rearrange this data such a way that minus delta P versus L will be plotting, right. Here actually minus delta P versus Q is the experimental data. Now, what we do for whatever the Q is there, that you convert into the velocity, right. So, then for each length of the pipe you have the different velocity. So, different 8 V by D values will be there. So, each length of the pipe, capillary pipe, you get 8 V by D, and then that for each L value, this minus delta P versus L you plot for different 8 V by D values. So, then you will have a curves like this. Here also we can see for a fixed length of the capillary, when the velocity is increasing, that means 8 V by D is increasing, what happens, pressure drop is also increasing. What we have to get from this rearrangement of data, minus delta P versus L you have to rearrange for each 8V by D value. Then whatever the plots are there, you extend them to get their intercept values, and then corresponding intercept values whatever are there, you note them as minus delta P E, you note them as minus delta P E, that is entrance correction for the pressure drop. Whatever the non fully developed flow conditions existing at the entrance, right, because of that one pressure drop is increasing, right. So, how much is that pressure drop is increased is nothing but this minus delta P E. So, from the experimental minus delta P, you have to subtract this minus delta P E to get the corrected minus delta P C or corrected pressure drop. That minus delta P C should be used in the expression tau W is equals to minus delta P by L R by 2. Here in place of minus delta P, you have to use minus delta P C, where minus delta P C is nothing but minus delta P minus of minus delta P E. So, whatever experimental pressure drop is there, that is showing more pressure drop compared to the fully developed condition pressure drop. So, from how much is more? This minus delta P E, whatever value is there, this is the more value. This more additional pressure drop value, that has to be subtracted from this one. So, that will be giving the corrected pressure drop, and that corrected pressure drop should be used in the shear stress expression, right. Now, we take an example on this problem so that we can understand better, but before going to the example problem, let us see the possible disadvantages of this method, right. First of all, it is cumbersome, and you have to do more number of experiments. In general, for any applications, usually you have one particular capillary and then try to do the rheological measurements, etc., using one capillary only. Now, here you have to get more than at least 3 capillaries having same diameter but different lengths. That is what you have to find out. So, that is a kind of laborious, and then we have seen this minus delta P versus L plots, whatever we have drawn here, they are shown kind of linear plots. But in general they may not be linear. Why they may not be linear in general for all fluids or for all cases? Because here we are incorporating, we are checking for only source of error due to the entrance effect, but there may be other sources of errors also, wall slip. So, that may also contribute something, and then because of that one, this minus delta P versus L plot may become non-linear, right. So, sometimes if the fluid is time dependent fluid behavior, that may also cause some effect. Viscous heating also have some kind of effect. But most importantly, we are making corrections for the pressure drop, and then if the viscosity of the fluid, test fluid itself is having viscosity dependent on pressure, then the reliability of this method would be very much lesser. So, this is very much another important factor, and also capillary, if it is too short, then flow to be become fully developed is not possible. So, that is another possible source causing this minus delta P versus L plot not to be linear. Okay. So, out of these errors, the pressure dependent viscosity causes usually positive deviation from the linearity, right, when L by D is large, and then wall slip, time dependent behavior and viscous heating may cause a kind of negative deviation from the linearity of minus delta P versus L. So, coming to the example problem, the data shown in this table, it is given minus delta P versus velocity of the ram for different lengths of capillary, and then it is obtained for a 4% CMC solution, CMC in water solution, using a constant flow rate rheometer, capillary rheometer, extrusion capillary rheometer. The diameter of the barrel is 23.3 mm, whereas the diameter of the capillary is 0.408 mm. Right. Here the velocity of ram is given. So, that means velocity of the fluid in the barrel, whatever is that velocity is given. but in our analysis the velocity terms are the velocity of the fluids flowing through capillary velocity it should be, right. So, that we have to make consider, and then for each velocity for different L values of capillaries, right. So, now this is L1, this is L2, let us say this is L3, minus delta P information is given in this tabulated column in kilopascals, right. So, now the question is the obtain the shear stress versus shear rate information for this polymer solution, neglect the friction in the barrel and then establish the magnitude of end effects, right. So, this is the statement of the problem. So, what we have to do, first of all we have to find out what is the capillary velocity or the velocity of the fluid flowing through capillary, not through the barrel, right. So, because that velocity, that average velocity of the fluid flowing through capillary, that is what we are going to use in calculation of the shear rate. Okay. So, now we can use the continuity equations, right. So, that to get the velocity of the fluid in the capillary using this velocity of the fluid in the barrel. So, that is continuity equation if you use pi by 4 dB square V ram is equals to pi by 4 d square V, where dB is nothing but the diameter of the barrel, d is nothing but the diameter of the capillary, V ram is nothing but the barrel velocity and V is nothing but the capillary velocity, right. So, now here except V everything is known, right. For the first data point where V ram 0.09 mm per second, the corresponding V from this equation we can get it as 0.294 meter per second, 0.294 meter per second. So, the corresponding nominal shear rate using this V value for the first data point is 8 V by D. V is 0.294 meter per second and then D capillary diameter is 0.408 mm. So, into 10 power minus 3. So, this comes out to be 5755 second inverse, right. And then here the statement itself mentioning establish the magnitude of end effects. So, it is already stating that there is a kind of end effects, we have to make an kind of magnitude, how much is that magnitude of that end effect, that we have to find out. So, we directly need to calculate tau w using minus delta P c, right. So, minus delta P c is nothing but minus delta P minus delta P e, this we have to find out. This we have to find out from the plot minus delta P versus L for different 8 V by D, right. So, first of all what we have to do, whatever this data is given V ram, corresponding V capillary, that we have to find out and then rearrange the table. So, first point we have find it as 0.294 meter per second. So, what we have this table. So, when V ram for length of the pipe L1 49.5 mm, V capillary we have already seen obtained it as 0.294 and then corresponding 8 V by D is 5755, right, and then corresponding experimental minus delta P value is 448.16 kilopascal, that is given already, right, that is already given. So, this point like this we have to for each V ram values what is the corresponding V velocity for each L value and then corresponding 8 V by D we have to check for the L1, L2, L3 also, right. So, these things we have to find out using the previous slide correction examples whatever we have done using them, right. Now, what you do after getting this thing, from here itself if you can plot minus delta P versus L for each 8 V by D, that is fine. When 8 V by D is 5755, minus delta P is 448.16, L1 is 41.5 and then here minus delta P is 655 and then L2 is 74.5 and then here minus delta P is 882.5 and then this is 99.5 L3. Like that if you plot, so each delta 8 V by D. So, this line, the bottom most line indicate 8 V by D is equals to 5755 second inverse. So, minus delta P versus L we are plotting when 8 V by D is equals to 55 for L1 whatever the delta P is there, L1 is 49.5 mm right, corresponding delta P is 448.16, this is the data point. And then when 8 V by D is equals to 5755 for the second pipe where the length is 74.5 mm, the corresponding delta P value is this one 655, this is 655 kilopascals. Similarly, when 8 V by D is 5755, for the case of third capillary having a length 99.5 mm, the corresponding delta P is this one 882.5. Like that for other values of 8 V by D also you have to plot, and then all these lines you extrapolate to L is equals to 0 line here, right. So, then here the corresponding values intercepts whatever are there, they are nothing but minus delta P E, they are nothing but minus delta P E. So, from this intercept for the first case when 8 V by D is equals to 5755, minus delta P is nothing but 14.6. For second value of 8 V by D, minus delta P is 15.1. For third value of 8 V by D it is minus delta P is 28.1 from whatever the intercept values. Similarly, for the fourth value of 8 V by D, minus delta P is 52.7 kilopascals, and then for last value of 8 V by D we have this minus delta P is 63.1. Now, in order to get the delta PC, from this delta P you subtract 14.6, so then we have minus delta PC. Similarly, from this value also you subtract 14.6, so then another value of minus delta PC. Like that from this value also you subtract 14.6, so then you have the another value of minus delta PC. So, for all these pipes, so then corresponding delta PCs are obtained here. So, using those delta PC, let us say first point we have this tau W is this one, tau W is equals to minus delta P E multiplied by D divided by 4 L, minus delta PC by L D by 4. When you substitute here all the values, now you get tau W is equals to 893.4 pascals. So, all those corresponding tau W first value we have calculated 893.4 pascals. Likewise, we have to obtain all other values and then tabulate here. What we can see here, 8 V by D is same 5755, 5755, 5755, almost close to them. So, similarly like this also other values of 8 V by D, but the corresponding tau W values they are not exactly same, but they are very close. The whatever the scattering is there very small, like let us say here 1150 approximately, here 1160 approximately, it is 1120 approximately. So, what we can do, we can take the average of these three values and then you write this average value of tau W here, or before taking the average value also, if you plot this tau W versus gamma dot or let us not call gamma dot, it is 8 V by D nominal shear rate. So, here you can find these things are almost superimposing onto the same curve, indicating that now this new or the true value of shear stress has been corrected with the entrance effects. So, now you can average it so that you can have the tau average value of these things, okay. And then this is 8 V by D, right, but this is not, this 8 V by D values are not the true shear rates, right, they are the nominal shear rates. So, you have to find out the true shear rate gamma dot W is equals to 3 n prime plus 1 by 4 n prime 8 V by D, where n prime is equals to d ln tau W by d ln 8 V by D. This is what we do. So, whatever this average tau average versus 8 V by D information is there, right, this you plot on a log graph and then grade the slope. So, you will understand this as n prime is nothing but 0.275. Now, whatever 8 V by D values are there, you multiplied by factor 3n prime plus 1 by 4n prime in order to get the true shear rate, right. So, this is how we have to make corrections for the entrance effect, right. Exit effects are there is no correction method available, and in general they are assumed to be small or negligible compared to the entrance effect, especially when the length of the capillary is large enough. So, next one is the wall slip effects. Wall slip effects in general may occur in the case of non-Newtonian multiphase concentrated suspensions, foams, emulsions, polymers, etc., especially when they are allowed to flow through narrow passages. Narrow passages like porous rocks, etc., or porous medium, or very small diameter capillaries, etc., then it is possible that this fluid may experience some kind of slip at the wall. They will not be having zero velocity at the wall, but they will be having some velocity, right. So, what happens, why this slip velocity occur? As I already mentioned, in such narrow passages, whatever the fluid layer, let us say this is the center of the pipe, capillary pipe, there is whatever the first layer of the fluid attached to the surface, that will be depleted, right. In general, this depleted layer having the viscosity smaller compared to the bulk viscosity of the fluid, or the velocity viscosity of the fluid in the other region, right. So, because of this change in viscosity, whatever the velocity supposed to be 0 at the wall, it will not be 0, but the depleted layer would be moving with much higher velocity compared to the 0 velocity. Okay. So, the concept of apparent slip at wall has proved to be of value in explaining anomalous effects, because researchers have found, even after incorporating these end effects, then whatever the rheological curve tau w versus 8v by d or tau w versus gamma dot w, they are not superimposing onto the same curve. So, this is the one of the reason later on they found, because of this slip velocity, especially very narrow diameter capillaries, these anomalous results are found for non-Newtonian systems, right. So, then what are the applications, like where in general we find this apparent slip in engineering, especially chemical related engineering disciplines, in general in food processing applications, and then some narrow opening flow areas like concentric cylindrical viscometers, parallel plate viscometers, cone and plate viscometers, narrow opening capillary viscometers, etc. All these viscometers, the passages is very narrow. So, then definitely in such cases there will be a kind of slip velocity. So, then other applications are extrusion of pasty materials, flow of macromolecular polymer melts and solutions in narrow gaps, etc. These are the only few of the cases where this apparent slip can be encountered, but in the case of non-Newtonian fluids, even the flow area is not very narrow. Then also some recent research results have been indicating that there would be a kind of possible slip velocity for especially viscoplastic material, even if the flow area is not very narrow, right. So, this phenomena of slip is in general associated with the flow of structured materials in narrow gaps, such as porous media, microfluidic devices, extrusion dyes used in food and polymer processing applications, etc. Right. Presence of depleted layer near wall is responsible for a high flow rate than expected at a given value of wall shear stress. So, let us say in general, whatever if this is the pipe wall, whatever shown here like this is the pipe wall, and then let us say this is the center of the capillary pipe. This is the center of the capillary pipe. In general, what we expect the velocity to be 0 at the wall, because of the no slip conditions, whatever the layers of the fluid are attached to the surface having the velocity same as the wall velocity. So, now here in this case 0 velocity, because the pipe capillary is not moving, right, and then gradually as we move towards the center of the capillary, velocity increases, right. This is what expected in general for Newtonian fluids or any fluids where there is no slip velocity, but very small size capillaries, and especially for non-Newtonian fluids, it is not true because of the depleted layer at the wall that is having very small viscosity compared to the its bulk effective viscosity. At the wall it will be having some velocity, and then after that it gradually increases anyway in the similar manner as in the case of other cases. So, this because of this high velocity, that is what mean by the molecules at the wall of the capillary, they are moving at a much faster rate compared to the previous case where there is no slip velocity, and then because of this one, whatever the shear rate you calculate under these conditions, that will be very much smaller compared to the shear rate when you assume no slip conditions. So, that means here now we have to find out if at all these wall slip effects are existing, we have to find out what is the slip velocity, and then that slip velocity we have to subtract from the velocity got from the experiment. Whatever the experiment's Q information is there, that you convert into the velocity. That velocity, from that velocity this slip velocity has to be subtracted, then only we can make the correction for the slip velocity, because whatever the working principles that we have developed for the capillary viscometer, they are for the fully developed flow, but but having the no slip boundary condition at the wall. That is what we applied in the previous lecture if you recapitulate, right. But that is not true from this thing. So, it is causing some additional velocity. So, this additional velocity has to be subtracted from that experimental velocity values, then that V minus Vs has to be used in the nominal shear rate or true shear rate calculations. Okay. So, we have to get back to the working principles derivation. Wall slip in the context of capillary viscometers. So, wall slip may give rise to inconsistent wall shear stress versus apparent wall shear rate data obtained with capillary tubes of different diameters, even data when have been corrected for all other known effects. Even after incorporating, as I mentioned, even after incorporating end effects, there are some kind of anomalous, and those kind of anomalous inconsistency in the results may be because of this slip velocity, right. So, we have to quantify effect of wall slip by assuming that the slip velocity exists. So, volumetric flow rate for the flow through capillary pipes that we have seen dq is equals to 2 pi r Vz dr. Now, if you integrate it, 2 pi r Vz dr, Vz is also function of r, and then there is a r. So, when you integrate 2 pi, you can take common, integration of r is r square by 2 Vz plus integration of r is r square by 2, and then differentiation of Vz is dVz by dr, but since we are writing plus here, so it minus has to come, otherwise it should be minus here and then plus here. We are writing minus here because this minus dVz by dr indicates the kind of shear rate information. Okay. So, that is the reason we are writing, that is the shear rate decreasing with increasing r values. Okay. This is what we have seen. Now, when you apply the boundary conditions, what we have, first term, when we apply the limits, lower and upper limits, we have these terms like lower limit 0, upper limit r, capital R. For the first term when we apply, so r square by 2 Vz at r is equals to r minus r is equals to 0 is the lower limit. So, 0 square by 2. So, this term is anyway 0. While developing the working principles, what we have taken? We have taken this Vz at wall at r is equals to capital R is also 0, and then altogether this first term was not there, only the second term was there, right. But now we understand there is a wall slip that is going to influence the rheological parameters significantly. So, we cannot take, we know now there we are considering the effect of the slip velocity. So, at wall now r is equals to r, rather no slip velocity, we have a slip velocity, that slip velocity let us indicate as Vs. Let us indicate that slip velocity as Vs. Then the volumetric flow rate is nothing but this particular expression. So, it is not the only second term as in the working principle. In addition to this one, there is a correction because of the slip velocity. Okay. So, this is the first term in the RHS is associated with the velocity slip. and then second term is associated with the no slip velocity condition Qns. Qns, that is second term, is equals to pi r cube by tau w cube integral 0 to tau w tau rz square f of tau rz d tau rz. This we have already derived in the previous lecture, so we are not going to derive we are not going to do it again, right. So, but however, rather doing substituting this particular term here in the second term in the RHS of equation 1, this entire thing we will write it as Qns. We will not substitute this expression here for our convenience, because we know for a given shear stress value this Qns is constant. Okay. So, we write this particular term, second term in the RHS as Qns, and then both sides what we do, we divide by pi r cube tau w either side. Then we get this q by pi r cube tau w is equals to Vs by r tau w plus Qns by pi r cube tau w. Q you write in terms of the velocity, average velocity, and then multiply by the cross section area, right. So, then simplify, you will get q by pi r cube is equals to 2V by d. So, q by pi r cube, q we can write as V multiplied by pi r square cross section area divided by pi r cube. So, V by r we can write it as 2V by d, right. This is what we can write here, and then multiply both sides by 4. So, that left hand side in place of q by pi r cube we have 2V by d multiplied by 4 8V by d, 1 by tau w is as it is. Here also you convert in terms of d. So, 2 Vs by d, and then we are multiplying by 4. So, 8 Vs by d 1 by tau w as it is, and then this particular term Qns as it is, pi r cube we convert into the d terms, and then we are multiplying by 4. So, we have 32 Qns by pi d cube tau w. So, whatever this second term in RHS is there, that is constant for a fixed value of tau w, we know. We know that it is constant because because of the no slip condition. Okay. Now, what we can do, we can plot 8V by d versus 1 by d. 8V by d versus 1 by d, when we plot, we can have a linear plot having the slope 8Vs. So, from the slope of 8V by d versus 1 by d, you can get the information about the magnitude of this slip velocity Vs. So, that Vs you should subtract from V to get the apparent shear rate. So, that is apparent shear rate after incorporating the slip effect is nothing but 8 into V minus Vs by d, right. So, in order to incorporate the slip velocity, in order to get the true rheological behavior in the case of different capillaries of different diameters, you first need to find out this Vs. Once you find out the Vs, that Vs has to be incorporated here. Now, we take an example under this wall slip conditions, right, how to incorporate this wall slip conditions. So, a capillary has been taken of length 374 mm, right, through which 0.5% partially hydrolyzed polyacrylamide in water solution is passing through. They have taken 4 capillaries, length is constant 374 mm, but diameter is changing. D1 is 0.191, D2 is 0.266, D3 is 0.626 and D4 is 1.1 mm, right. So, the question is to obtain the true shear stress versus shear rate information for this polymer solution. Assume the end effects are negligible as the minimum value of L by d. From here the minimum value of L by d from here is 374 divided by 1.1 is approximately coming 340, which is much higher than the minimum L by d ratio of 100 value. So, it is expected that the end effects may be playing negligible role in this case. So, slip effects we have to find out. For these different d values for capillaries of different diameters, Q versus delta P information is provided here in a tabulated column. What we have to do first, we have to convert this Q versus minus delta P information in terms of 8V by d and then tau w. Then we have to plot tau w versus 8V by d. If they are superimposing onto each other all 4 curves, then we can say that there is no wall slip effect, right. If they are not superimposing onto each other, we must realize that the diameter of the capillary having significant role, and then it is causing some kind of elastic slip for some of these capillaries, or maybe for all of these capillaries of different diameters. So, those corrections we have to make. So, let us first convert this information in terms of tau w is equals to minus delta p by L d by 4, and then nominal shear rate gamma dot w n is equals to 8V by d. So, when we do all these things are given here. So, tau w for the first data point comes out to be 5.83 pascals, and then average velocity 4q by pi d square, that we can get here. Okay. So, gamma dot w n is equals to 8V by d is nothing but this one. So, 53.5 second inverse. So, 53.5 second inverse is the nominal shear rate for the first data point of the first capillary of diameter 0.191. Likewise, for all data points of each diameter capillary, we have to convert this information. When we do it and then convert it present it in tabular form, we have these values for different tau w and 8V by d values. So, now what we have to do? We have to plot this tau w versus 8V by d and then see if all of them are superimposing or not. When we plot, we can say that they are almost kind of superimposing for small values of 8V by d, but as we go towards the higher shear rate, they are not superimposing to each other. When you are changing the diameter of the capillary, you are not getting the same tau w versus gamma dot curves. That means that is even though having the large value of length of the capillary, you are not getting same curves. That means the effect is because of the wall slip velocity, right, because all other sources of errors are expected to be very small. Now, we have to do correction for this particular wall slip effects. Now, we are going to find out what is the slip velocity, right. For slip velocity, we have to plot 8V by d versus 1 by d curve, right. So, first what we do, we select 5 different values of tau w, let us say 5, 10, 15, 20, 25. Tau w is equals to 15. So, what is the corresponding value of 8V by d for each of these curve? Each of these curve is indicating some kind of some size of the pipe. So, let us say the black one is 0.191 and this one is 0.266 and this one is 0.626 and this one is 1.1 mm. Let us say for tau w is equals to 15 pascal, 8V by d for smallest diameter capillary is 529, next is 456.6, next is 362.3, next is 316.7. Like that, for different values of tau w values, we have to get this information, right. For each tau w value, 8V by d versus 1 by d, we are going to plot. 8V by d versus 1 by d, when we plot for each value of tau w, you can have a kind of almost linear plots, except the this one case of large shear stress. Then then what we have, we get the slope of each of these lines, 8V by d versus 1 by d for different tau w. When you plot, you get the slope of each line. So, slope is nothing but 8Vs. So, that 8Vs values for each curve is for each tau w is given here. So, corresponding Vs values are calculated and provided here. We can see from here that as the shear stress increasing, the wall slip velocity is increasing further larger. So, Vs versus tau w you plot, right, then you can have a curve like this. We can see for small shear stress almost Vs is 0, almost, that means no slip velocity may be assumed, but as the shear stress further increasing, the velocity is substantially increasing, and then when you make a curve fitting you get Vs is equals to this expression as function of tau w. Now what you do after finding out this Vs, that whatever the tau for each capillary diameter we have this tau w versus 8V by d, we already converted data, q versus delta minus delta p, we converted tau w versus 8V by d data. Now from 8V by d, from V what you do, you subtract this Vs value and then recalculate what is 8V minus Vs by d for each capillary diameter. So then you have this thing, right. For instance, for the first data point when d is equals to 0.191 mm, tau w is 5.83, Vs is 0.59. So whatever the 8 V minus Vs by d would be 28.9 second inverse. See the difference, earlier it was 53.5, now it is 28.9, almost reduced to the half, almost reduced to the half. That is what we have seen when the wall slip is playing role, the shear rate, nominal shear rate is expected to be much smaller compared to the nominal shear rate when the wall slip effects are not included. That is true for almost all cases kind of thing. Okay. So now this tau w versus 8 V minus Vs by d you plot and then check now if they are superimposing or not. Previously when we plotted tau w versus 8 V by d, they were not superimposing onto each other. Now after incorporating this velocity slip, you plot tau w versus 8 V minus Vs by d and check whether now are they superimposing or not, so that to make sure that the velocity slip effects are properly incorporated. When you do that one, you get this plot. So tau w versus 8 V minus Vs by d, if you plot here, now for each value of d diameter you can see almost all of them are superimposing onto the same curve, right. That means now the wall slip effects, after incorporating the wall slip effects, whatever the shear stress versus nominal shear rate information is there, that is giving the true rheological picture. So now you do not have any ambiguity which diameter of the capillary should be taken, because after incorporating this velocity, slip velocity, all of them are superimposing onto the same curve. So then you can select any of them, any of these capillary diameter as a reliable information. But however, this shear rate here is shown the corrected nominal shear rate, but it is still not the true shear rate. You have to find out what is this n prime. N prime is dln tau w by dln 8 V minus Vs by d. This is what you have to find out. Plot the same data in logarithmic coordinates, then get the slope. So you will find out this n prime is nothing but 0.44. Then the true shear rate gamma dot w would be nothing but 3 n prime plus 1 by 4 n prime multiplied by 8 V minus Vs by d. This would be the true shear rate. So this is how we have to incorporate. So what we have seen how to make correction for two major sources of errors in capillary viscometers. One is the end effects, another one is the wall slip effects. Okay. So let us say other thing, if you have data like this, when you plotted wall shear stress versus nominal shear rate, you have a data like this, smooth curve like this. After this, suddenly change in slope you can see. This change in slope here also for different kind of diameters, we can see. Before that one, all diameters are having almost same values, following the same line. After this line, the sudden change in slope is there. So this is because of after this value of shear rate, whatever the corresponding velocity is there, so that velocity is falling into is going beyond the laminar flow condition. So this is the other possible source of error, because of the flow is not being within the laminar flow conditions, right. So how to make adjustment for these kind of errors? simply you can discard this data from the point where sudden change in slope is occurring, because that is because of the flow is not being in the laminar flow conditions. Okay. So, finally, what we can say, it is appropriate to add here that in principle equations developed for capillary viscometer can also be used for viscoelastic fluids, but in practice considerable confusion exists regarding the end effects and from dye swell at the exit end of the capillary. So, there is a, though in principle these whatever the working principles of capillary viscometers are there, they can also be used for the viscoelastic material, but how much should be L by D value, how to incorporate the correction for the end effects etc. are not known for the viscoelastic fluids. Also in the viscoelastic fluids, we know at the end, at the exit point, a kind of dye swelling things are existing. We have already seen in the introduction lectures of viscoelastic fluids. So, how to incorporate those effects, all information are not available in those kind of effects. So, there is still some kind of ambiguity of using this capillary viscometer for viscoelastic fluids. So, the information and example problems provided discussed here in this lecture are primarily taken from this reference book, Non-Newtonian Flow and Applied Rheology by Chabra and Richardson. Thank you.